Welcome to another Mythology video. If I were to wake you up in the middle of the night, I'm sure that most of you would be able to rattle off the quadratic formula. Minus b plus or minus the square root of b squared and so on. But along with all that quadratic fun you had in school, most of you would have tortured a few carefully cooked up cubic equations and maybe even a quartic or two, right? But did you ever wonder why no one ever taught you the cubic formula or the quartic formula? Did your teachers ever even mention the higher degree counterparts of the incredibly useful quadratic formula? Probably not. Why is that? Is it a cultish mathematical conspiracy? Are they all hiding some deep dark secret? Well, today's Mythology is your invitation into the hidden polynomial brotherhood. Okay, here's the general cubic equation which we want to solve. And here's its solution, the cubic formula, in all its glory. Whoa, that looks interesting. So maybe that's our answer right there. That's way too complicated to memorize and use. A pretty good reason not to teach it, right? Wrong. Sure, the full cubic formula doesn't exactly roll off the tongue, but it's not that hard to make sense of. For starters, the two monsters inside the cube roots actually only differ in a minus sign. But we can also simplify things dramatically by some straightforward pre-processing. The general cubic equation can be reduced to solving a much simpler cubic with a genuinely simple cubic formula. What do I mean by pre-processing? Well, first, if you divide by the leading coefficient a, that gives an equation with the same solutions, but with a leading coefficient of 1. So we may as well turn all the a's into 1s. That already looks a lot simpler. The next most frequent coefficient in the formula is b. Now it'd be good to get rid of all those b's, and it turns out we can. There's a second easy pre-processing step which I'll motivate soon. This pre-processing allows us to assume b equals 0, and so we just have to worry about solving a simpler cubic without the green quadratic term. Pretty simple, right? Maybe not kindergarten simple, but definitely not a big leap from the quadratic formula. Again, by performing some simple pre-processing, we can reduce any cubic equation whatsoever to solving one of these simple cubic equations. In the literature, the letters C and D are usually replaced by the letters P and Q. And when people say cubic formula, they usually have this exact formula in mind. Really very pretty, isn't it? Okay, let's do a quick example to see how it all works. Let's choose, well, let's see, p is equal to minus 15 and q is equal to minus 126. Sub these numbers everywhere and we get this. The number under the square root sign pans out to be 3844, which happens to be equal to 62 squared. Lucky, huh? Now, 63 minus 62, that's 1, and 63 plus 62, that's 125. Cube root of 1 is 1, and cube root of 125 is 5, and so we finally get, so 6 is the solution of our cubic, and you can easily check that. Great! Although, shouldn't there be 3 solutions? What happened to the others? Don't worry, we'll get to them later. Anyway, all this looks pretty straightforward and very useful for dealing with cubical conundrums. Also, for people interested in how our mathematics came to be, the discovery of the cubic formula is considered to be one of the major milestones in the history of mathematics. So once again, why doesn't anybody teach the cubic formula? There are a couple of answers to this puzzling question, one more surprising than the next. Promise! Of course, I'll explain it all in the following. As you've probably already guessed, this is another masterclass Mythology video. And as usual with these long videos, we'll start really easy and slowly build up to the challenging finale. It's all broken up into 7 chapters with truckloads of really interesting cubic maths ahead. Plus, at the very end, I'll throw in solving the quartic equation for free. Mathematical seatbelts on? Okay, here we go. The cubic formula was discovered independently by 2 Italian mathematicians, Niccolò Tartaglia and Scipione del Ferro. And then, neither del Ferro nor Tartaglia told anyone about their amazing discovery. Huh? Why not? Well, just like today, the success of a 16th century mathematician depended on the sorts of problems they could solve. But back then, there was no such thing as publish or perish. Instead, mathematicians competed for celebrity in mathematical duels. Mathematicians would publicly challenge others with take-home exams. They would post sets of problems, and whoever could solve more problems was declared to be the better mathematician. And so, if you were the only mathematician with a secret weapon, like the cubic formula, then you would have been pretty much invincible. Don't tell anybody. Makes sense, right? And also an impressive start to 500 years of not teaching the cubic formula. Anyway, after winning a competition featuring nasty cubics, it became clear that Tartaglia had the secret weapon, that he knew the cubic formula. Then the great Girolamo Cardano started going after him for this formula. Cardano was a fascinating character, a polymath with his fingers in everything. He was a famous doctor, a top mathematician, a successful gambler, and so on. Anyway, eventually Tartaglia gave in. Interesting tidbit, Tartaglia gave Cardano his formula dressed up as a poem. Quando quel cubo con le coso appresso se agguaglia a qualche numero discreto, truan due altri differenti in esso. I'll put a link to a translation and discussion in the video description, okay? Tartaglia also made Cardano swear a solemn oath not to tell anybody else, which of course Cardano broke. After learning the formula from Tartaglia, Cardano kept digging and eventually also found the cubic formula in a notebook of Del Ferro, that other discoverer. It became apparent that Del Ferro discovered the formula before Tartaglia. In Cardano's mind, this meant he was now off the hook. He could now tell people about Del Ferro's solution, and he actually subsequently published a book about it. In a way, Cardano's book was like a Renaissance WikiLeaks, and similar to today, and not surprisingly, Tartaglia was incredibly annoyed by this WikiLeaking, and all hell broke loose. I'll link to some sources that have the complete story, which, apart from all the maths, also feature a murder, a beheading, and a cameo appearance of the Inquisition. An absolute must-read for all you math history buffs. Some great history, right? Now, I'd like you to imagine that we've all been transported back to the time of Cardano and his friends. Trying not to be distracted by all the beheading and inquisitioning, and armed with our knowledge of modern high school math, we want to challenge one of these big shots to a mathematical duel. But since they did not tell us about the cubic formula in school, we first have to rediscover it for ourselves. Time for a bit of a revision of quadratics to prepare ourselves for the cubic monsters to come. How do you find a solution to this quadratic equation? Sure, it's a no-brainer. Just plug the coefficients 2, 8 and minus 6 into the quadratic formula. Another way of finding the solutions, taught in school since time immemorial, is completing the square. This actually translates into the way of deriving the quadratic formula from scratch. Let me show you a methodologized version of completing the square for this particular quadratic. Okay, start by dividing through by the leading coefficient 2. All right, getting there, yes. Next, interpret x squared as the area of an actual physical square with side length x. Similarly, we'll think of 4x as the area of a rectangle with sides x and 4. Chop the rectangle in two, like so, and rearrange like this. Adding a little square in the top right corner completes the left side into a new larger square. But of course, to keep our equality, we also have to add the little square to the right side. Like that. The left side is not just square shaped, it's also a perfect square, namely x plus 2 all squared. It's now easy to solve the new equation, right? Piece of cake. Of course, there's also that second minus root 7 solution, which we get if we're not dealing with physical squares. Anyway, here's an animated derivation of the quadratic formula for the general quadratic equation by completing the square. Enjoy the animated algebra and the music. So we know how to complete the square geometrically in terms of real squares. This is actually similar to how Cardano and his friends, and probably also the Babylonians thousands of years ago, would have thought about the process. Algebraically, completing the square boils down to starting with this other super famous identity here. Hammering the quadratic to look like the right-hand side, and then using the squareness of the left-hand side to solve the equation. You've all done some version of this a million times, right? To continue our preparation for the cubic puzzling to come, we need a second, visual derivation of the quadratic formula. This very nice derivation also illustrates the geometric meaning of the quadratic formula. Ready? Okay, to be able to quickly refer back to it, let's write the quadratic formula in this form and tuck it away up there. Start again with the pre-processed form of our equation down there. Then the quadratic corresponds to a parabola like this. Here's a nice idea. The parabola has a special point, that turning point down there. Let's shift the parabola horizontally until the turning point rests on the y-axis. Shift, shift, shift. The two blue points, the x-intercepts, are still exactly the same distance apart. However, the quadratic for this new parabola is now in this simpler form, super simpler form, really. Right, it's just the archetypal y is equal to x squared parabola, just shifted up or down. It's easy to solve this equation, which amounts to locating the blue intercepts. And now, to find the solutions we are really interested in, we simply have to undo the horizontal shift we executed before and keep track of where the blue points go. There. Great. Okay, now let's see this scheme in practice. First, how far do we have to shift? Well, that amounts to figuring out the x-coordinate of the green turning point, right? Yeah, that one. This would normally be done in school with a little algebra. But we're on a mission here. So let's take the express lane and use a little easy calculus to make short work of this job. If you haven't seen calculus yet, doesn't matter. Just run with it or substitute the school algebra, okay? Okay, so form the derivative of the quadratic. Set this derivative equal to 0 and solve for x. There, solve, solve, solve. That's the x-coordinate of the turning point. And more than that, it's also the familiar minus b over 2a, the first orange term in our quadratic formula. So that's just a shift, right? Now we can shift our parabola. To obtain the quadratic equation of the new shifted parabola, we replace every x by x minus b over 2a. Maybe ponder that for a second? All good? Great. Now use algebra autopilot to expand and collect like terms. Neat. Of course, you also recognize the fraction, the messy constant term, right? There, it's in the green bit. Now solve to find the shifted blue points. There. And finally, undo the shift. Ta-da! Also very nice, isn't it? Okay, having re-expertised ourselves in quadratics, we are ready to confront our cubic nightmare. A very natural idea is to try and mimic completing the square, to somehow complete the cube using this perfect cube formula. Well, the way things line up sort of feels it might work, right? I think most people would play around with this for a while before trying anything else. Okay, so we'll really go for it for a day, trying to make completing the cube pan out. And we come up with zilch. It turns out it's not that easy, and maybe it's time to try something else. So let's look to mimic our parabola shifting. Okay, start the pre-processing by dividing by the leading coefficient. Graphically, this kind of cubic will look roughly like one of these curves. A cubic equation always has at least one solution, but may also have two or three. As well, every cubic has one special point, the inflection point. This is the point where the cubic switches from curving one way to the other. Finally, and this may come as a surprise to many of you, a cubic graph always features a half-turn symmetry about this special inflection point. Now, let's shift the inflection point to the y-axis. For that we need the x-coordinate of this point. I'll again use some baby calculus. The inflection point here is characterized by the second derivative being 0. So differentiate once, okay, twice, set equal to 0 and solve. Solve, 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 solve. Solved. That's it. That's the x-coordinate. This fraction minus b over 3a actually appears in the original monster cubic formula I showed you. Let me show it to you. There, that's the shift again. Now replace x by x minus b over 3a and let the algebra autopilot perform our shift. That finishes the pre-processing. The new coefficients are a messy combo of the original a, b, c and d, but the fundamental form is one of those simple cubics I mentioned in the intro. So if we can figure out how to solve this special simple cubic equation, then we can undo the shift to solve the original equation. All very natural and very pretty. I just love this stuff. Now to analyze our special cubic, what do P and Q stand for in the picture? Well, Q is just the y-intercept and P is the slope of the curve at the inflection point. So P is just the slope of this green line. Of course, changing Q just shifts the cubic up or down. What if we vary P? Well, here's an animation of how the shape of the curve changes. So what we've got here is that for negative p, we've got this roller coaster shape curve. And for positive p, it's kind of stretched out like that. All right, so again, going into the negative roller coaster. In a little while, it will be important to know how many solutions our equation has. Again, for non-negative p, the graph is stretched out like this, and there can only be one solution. But for negative p, we get a roller coaster graph like this, and 1, 2, or 3 solutions are possible. To figure out how many solutions we get for negative p, we need to determine the difference in height between the inflection point and the two extrema. Okay? Because of the half-turn symmetry, the two green height differences will be equal. Now, how many solutions will we have? Okay, you got it? Well, if the yellow segment is longer than the green, as pictured here, then there will be just one solution. It's also straightforward to check algebraically when this happens. How? Well, the extrema of the cubic occur when the derivative is 0, and the derivative of the cubic is a quadratic. And so we just have to solve a quadratic equation to pinpoint the coordinates of the extrema. Again, piece of cake, right? And with the coordinates of the extrema and the turning point, it is then also easy to translate the yellow-green inequality into algebra. I'll leave that as an exercise for you to complete in the comments. In the end, the algebraic counterpart to our yellow-green inequality pans out like this. Okay, in exactly the same way, the cubic having 2 solutions corresponds to equality here, and 3 solutions correspond to the reverse inequality. And so the sign of the expression q over 2 squared plus p over 3 cubed tells us how many solutions our equation has. And this does not only work for negative p roller coaster cubics that we've been considering so far, but for all cubics. Right? For example, if p is positive, we have only one solution. But also with p positive, q over 2 squared plus p over 3 cubed is positive. Works, one solution. But there's one tiny little annoying exception. Can you spot it? Well, can you? Well, when both p and q are 0, we still have only one solution. However, in this case, q over 2 squared plus p over 3 cubed is equal to 0. And so our table wrongly suggests there are 2 solutions. Now, this is a minor glitch in the fabric of the universe, which is easily fixed by talking, for example, about single and repeated solutions. Anyway, the takeaway message from all this is that q divided by 2 squared plus p divided by 3 cubed plays the same role for cubics as the discriminant b squared minus 4ac plays 4 quadratics. And just like b squared minus 4ac features prominently in the quadratic formula, we'll see that this cubic discriminant takes center stage in the cubic formula. Remember when we wasted that day trying to complete the cube? It turns out that time wasn't totally wasted. While playing with that perfect cube identity for hours, we noticed something very promising. The two middle terms have a common factor 3uv. If we pull it out, we get this. And now we can line up things like this. What this shows us is that if we somehow find u and v so that all the lined up boxes are equalities, then our cubic is effectively a perfect cube after all, and we will have solved our equation. What this amounts to is solving for u and v in the green and yellow boxes. And then, having done that, we obtain our solution x by just adding u and v. Pretty easy actually. Let me just show you one way of doing this. Well, first cube both sides of the green equation. Next, multiply the yellow equation by v cubed. Now we've got the same expression here and here, and we can sub like this. Shuffle everything to the left as usual. Looks bad at first glance, right? But it's just a quadratic equation in disguise. Think of the v cubed as the unknown. There, blue squared plus something times blue plus something equals 0. Now, just use the quadratic formula to solve for the blue v cubed. And cube rooting on both sides gives this. Almost there. Remember that in our original equations, u and v are indistinguishable. And so if we solve for u, we'd get exactly the same result. And now, because of the plus minus, it would seem we can make two choices each for both u and v, giving a total of 3 different ways to add them to get solutions to our cubic equation. Plus plus, minus minus, plus minus, and what gives the same sum, minus plus. So here we have 3 candidates for solutions. And cubic equations have up to 3 solutions. That looks very promising, doesn't it? Yes, it does. However, if we double check by substituting our candidates in the original equation, we find that only one, the plus minus or minus plus, gives us a genuine solution of the cubic. Why don't the other candidates for solutions work out? Can you figure out what the reason might be? Let us know in the comments. Also, if all this only gives one of the solutions, where are the other solutions hiding? Well, we'll get to that. Why don't they teach this? Well, there's a few related reasons that have to do with the way the cubic formula spits out solutions. Remember that really nice example that I showed you at the beginning? In that case, the solution given by the cubic formula easily simplified down to a final answer of 6. Lucky with all those integer squares and cubes materializing in just the right spots, wasn't it? Of course, it wasn't luck. One has to work damn hard to find an example where the roots simplify that well. But things in general are even worse than you might expect, and some really weird stuff can happen. Let's have a look at another example. It's pretty easy to guess a solution of this equation. Can you see it? Okay, too late. Yep, x is equal to 4. And just to check, 4 cubed, that's 64. 6 times 4, that's 24. 64 minus 24, that's 40. Minus 40 is 0. Bingo! But what does our formula tell us? Plugging in minus 6 and minus 40, we get this. So the cubic also has a monster rooty solution. But remember that 392 under the square root sign is our cubic discriminant. And since 392 is positive, that tells us the cubic equation has only one solution. But that means that the rooty monster in front of us must equal 4, the solution we guessed earlier. Can you see at a glance that the two sides of this equation are really equal? Not obvious at all. That's a challenge for you. Can you do this from scratch? But it can be even weirder. Have a look at this third example. Okay, plugging in -6 and -4, we get, well, under the square root sign, our cubic discriminant is 4 minus 8. That's -4, which is negative. Here you think. But let's first just focus on the negative discriminant, which tells us that our equation has 3 solutions. Let me just show you those solutions. But now have a closer look at the expression spat out by our cubic formula. Not only does this expression not look anything like those 3 solutions, in addition, it contains square roots of negative numbers. This means that even though our 3 solutions are real numbers, our formula expresses these solutions in terms of complex numbers. How crazy weird is that? Not surprisingly, Cardano and his buddies were completely weirded out by this. They barely had an understanding of negative numbers, and complex numbers were way beyond their imagination. And, as is clear from the formula, the case of 3 roots always leads to these weird complex number infested outputs. This horror case came to be referred to as the casus irreducibilis. In fact, the struggle to overcome the casus irreducibilis led to the discovery of complex numbers by Raphael Bombelli, not long after Cardano published the cubic formula. I'll make sense of the casus irreducibilis in the next chapter. First, let's just get all the cubic formula weirdness out of the open. How much weirder can it get? Well, let's see. When you're only dealing with real numbers, as we have until now, in the first instance it makes sense to speak of the cube root of this number, the one real cube root of this number. However, when we're dealing with non-real complex numbers, there is no distinguished cube root anymore. Just as every non-zero complex number has 2 square roots, every non-zero complex number has 3 cube roots, and none is distinguished in any way that makes it qualify for the job of the cube root. As we shall see, this means that the expression up there does not just stand for one of the real solutions down there, but for all 3 of them. One final bit of weirdness. So Cardano's formula outputs tame integer, rational, etc. solutions in weird complex ways. That prompts the question whether there is another, totally different cubic formula that avoids this weirdness, right? There's really no reason why there should not be several cubic formulas. The answer to this question is both no and yes. If by formula we mean a combination of the coefficients using just basic arithmetic and square roots and cube roots and the like, as in our cubic formula, the answer is no. Any such formula cannot totally avoid the complex weirdness. This can be proved using a heavy weapon called Galois theory. We skirted Galois theory in our previous video on impossible construction, and it will also be the topic of a completely insane, completely insane mathologer video in the near future. On the other hand, if we allow ourselves to also use a bit of trigonometry, then we can make up cubic formulas that always give real solutions in terms of real expressions, avoiding the detour into the complex numbers. Anyway, to summarize. Except for the overcomplicated output of simple solutions, our cubic formula is well suited to dealing with cubic equations that have positive or zero discriminant. That is, for equations that have exactly 1 or 2 solutions. We don't need to enter the complex wilderness. Okay, and that just leaves us with making sense of complex infested outputs in the case of negative discriminants. Here's one of the complex monsters we created earlier. Let's try to make sense of it. To begin, we'll just cross our fingers and go for it, without worrying too much about any worrying details. Again, if you've never seen complex numbers, please just run with it as best as you can. So we can always rewrite the square root in terms of the square root of -1, like this. Now, the square root of -1 is usually abbreviated by the letter I. And Martin behind the camera is shaping to throw something at me. Okay, yes, there's a large nit you can pick here, but please save your nitpicks and projectiles for the comments. In the end, it all works out okay. The 2 complex numbers under the cube root only differ by the plus or minus sign in the middle. That means They are complex conjugate numbers, and so in the complex number plane, we picture them on opposite sides of the real axis. These two complex numbers are also pinned down by this distance and this angle. That means we can rewrite our complex numbers in terms of sine and cosine like this. So there. Oh, beautiful. Ah, so nice. This way of writing complex numbers is called the polar form. To find the roots of complex numbers written in this form is very easy. First take the cube root of the distance, like so. Actually that simplifies quite nicely here. And then divide the angle by 3. Okay. There, roots coming up. Now, when we add up the two complex numbers up there, the plus minus imaginary parts cancel out, leaving us with a real number. That's one of our real solutions. But that's not all. So far, we've only used one cube root each for the two terms in Cardano's formula. There are 2 more each. All these roots together form the corners of 2 equilateral triangles with centers the origin. There's one, and there's the second triangle. In total, there are 3 conjugate pairs among our 6 cube roots. There. Add up these conjugate pairs to get all 3 solutions of our cubic equation. And just in case you're wondering, and this is a little trick challenge for you, not trick, trig, these numbers are equal to these nice expressions. Great stuff, don't you agree? I have to admit that these videos are always a killer to put together, but they're also a blessing. While preparing them, I always end up stumbling over lots of great maths and amazing history, of which before I only had the barest inkling. Always enough for another video or 2, which I know I'll never live long enough to get to. So in lieu of a second video, here are just 3 fun facts I stumbled across while working on this video, without explanation. Feel free to give proving them a go in the comments. Fun fact number 1. Here's a cubic with 3 zeros. Draw in the tangents at those zeros. The tangents intersect the graph in 1 more point each. Then those 3 points lie in a straight line. Always. Nice, huh? Fun fact 2. This is again about cubics with 3 zeros. Highlight the inflection point. Draw an equilateral triangle whose center is hovering somewhere above the inflection point. Then it is always possible to rotate and scale this triangle so that the 3 corners end up above the zeros. Pretty neat. You can prove this easily based on what I said in the previous chapter. But there's more. Inscribe a circle into the triangle, then the 2 extrema line up with the left and rightmost points of the circle like this. Final related fun fact, and this one is a real killer. Start again with a cubic polynomial, but this time the coefficients can be any complex numbers. So in general, the 3 zeros of such a polynomial will be 3 points in the complex plane, forming a triangle. Highlight the midpoints of the edges of this triangle. It turns out there's exactly 1 ellipse that touches the edges in those midpoints. And here's the killer fun fact 3. The 2 zeros of the derivative of our polynomial are the focal points of this ellipse. This amazing result is called Marden's theorem. And one more thing is true. The 0 of the second derivative, which is also the z-coordinate of the complex inflection point, is the center of the ellipse. And phew, that's just about it for today. To finish, I'll just show you an animation of a method for solving quartic equations. This solution is due to Lodovico Ferrari, Cardano's assistant. One of the super surprising and famous results in algebra is that Ferrari's method is as far as we can go when we are asking for solutions in radicals. There is no quintic formula of this type or a formula for anything beyond. As I said, proving this will be the mission of a future mathologer video. For now, enjoy Ferrari and the animations and the music. Until next time.